photons of light and atoms in the gas. He is also winner of the Creel Prize 2019. And also I came to know about Ofer from his seminal work on nonlinear quantum optics. And he's very actually kind of clear what he is speaking. That's what I like the most. And let me okay, so let me ask now Ofer to please start.
Thank you, Dibiandu. Thank you for the invitation. Thank you for the kind introduction. So indeed, today we're going to talk about a topic that is a bit different from, say, quantum nonlinear optics and other things Dibiandu and I did together, which is to talk about noble gas spins, gases of noble gases that have a non-zero spin, and we would like them to work for us and do some quantum optics and quantum technology with them. But I thought perhaps before I start, I will give you a notion of at least this other project in the lab. So you may know of this from Dibiandu, and one of the things that seem to be very, very attractive is this paper that we wrote together, in which we describe, and this is what those type of Rydberg polarities do, the effective interaction between photons that propagate together, and in our case, excite atoms that have dipole moments, and therefore effectively interact. So this system where photons effectively interact very strongly is an interesting system, as you may know. And I just kind of, just to briefly mention, and also to bring, for example, Dibiandu up to date with what's going on in this. So you could, for example, form different types of propagating photons of polaritons that excite different Rydberg states. And then you could have interaction between several flavors of photons, so that it's not a single photon flavor, but maybe two flavors of photons, so that it looks like an effective spin of photons. There is the possibility to get the photons to repel one another. And then actually, when they do that, they you see those oscillations in the correlation functions between them. They crystallize to some extent. So this is towards getting photons to order and become to get a crystalline order, a crystal. Or you could make photons attract each other and attract so strongly that they form molecules, and you can measure the bound state of these effective photonic molecules. And there is one bound state, and there is also a signature for a second bound state. And then you can go even further and measure effects that relate to three photons that are not strictly coming from the effect of two photon interaction, but they are somewhat new. So this is a very fun and exciting playground that we play with in my lab. So that was for a recap on what went on after this paper was published. And now we are going to our main subject. Okay. So we are talking about quantum optics with noble gas spins, but let's track back a bit, and let's start with quantum optics with alkali atoms, because this is much more well known. This will set the scene. Here are alkali atoms. You probably know them. Here is a rubidium atom, potassium atoms. We talk about those atoms on the left column of the periodic table. These are usually the main actors in this kind of setups. They have one electron in the outer shell, and this electron has a spin, and this is the spin that we like to work with. There is also orbital degree of freedom. That's another a property of the electronic wave function. And then there is the nuclear spin. So for example, if we sum them up, often we get a composite spin, a hyperfine spin that can be, say, 1 or 2, for example, for rubidium. These spins are very good. They are very useful. They are useful because from one hand, they can be very sensitive to external electric fields. And from the other hand, they could be very insensitive to external electric fields. And I'm showing you here two known examples for applications. So what you see on the left is a small miniature magnetometer made from alkali vapor at room temperature, where we use the fact that those electron spins in an external magnetic field process at a very well-known frequency, and they process fast. That's the gyromagnetic ratio of the electron. And you can use this precession frequency if you measure it optically in order to measure the magnetic field. So it functions as a magnetometer. On the other hand, there are other spin degree of freedom, like the transition, the hyperfine transition, which if you want relates to the flipping of a nuclear spin. And this is very insensitive to the external magnetic field. And so you can make a reference, a clock out of it. And that's another example for a miniature device that is based on alkali atoms, alkali vapor. So they are very useful and kind of you can produce from them applications in real life and pack them into nice small packages. So it would be very useful if we could also do quantum things with them, quantum optics, because then we could pack those quantum tools into small packages. And when people do quantum optics with alkali spins, the spin that is actually, the degree of freedom that they actually work with is the collective spin of the ensemble. Okay? So when I say the collective alkali spin, or more generally the alkali spin, I mean the spin, the operator that is simply summing over all the constituent spins. So we have all the atoms, and if we pump them and point them all upwards, we get a macroscopic spin, macroscopic polarization that points up. We can define an operator. And if the operator is in the classical state, then there would be this uncertainty disk that comes from the uncertainty principle. And that would be a state where the atoms are non-correlated. So non-correlated is the, if you want, the classical state. What would be a quantum state? The quantum state would be a state where there are correlations between the spins. This is one example. This is a spin squeezed state where the atoms, the correlations look like the atoms have conspire, or they agree to be less certain in one direction on the expense of being more certain in another direction. And that would be a squeezed state. It's a non-classical state. And here is another non-classical state of the collective spin. That's the Fock state with, for example, exactly one excitation of these spins. So that would mean that all spins point up, but one, we don't know which, it's a superposition, but one and exactly one points down. And it's again a strongly correlated state, because if we identify this one, we know what the state of all the other atoms. So this is the quantum creature, the quantum variable we are working with when we work with ensembles of gaseous spins.
Sorry, Ofer. So can we ask question in between, or
sure, please
okay.
Ask questions. That would be much more fun.
Okay, so now when you said the classical state or classical case for the collective spin, so these spins are for individual, I mean spins of each alkali atoms. So why should they behave together? Is it also you are saying that they form a many body state, a many body quantum state, that it still be considered as a large spin? What means how you got that large S or S spin?
So when we start the experiment, the first thing we do, we use some technique, usually an optical technique, to pump all the individual spins upwards. Okay, yes. We use optical pumping, for example, such that now if we had a billion atoms, all the billion spins are pointing up and not down. Okay. This is a state. It's not a strictly a many-body state, because it is just a product state of all spins pointing up.
Yes, so that's what I'm saying. But then still they do have collision between them and all this. So they have individual fetch factor for each spin. And
that is correct. So there are many mechanisms, usually relating to the external degree of freedom, the motion, that could hurt the spins. The spins the atoms move from one place to the other. Yes. They could collide with each other. They could collide with the walls. When they collide, the spins are not always conserved. The spins could be lost to an orbital angular momentum. So there are many mechanisms that are in the background. But if we, like in an ideal case, if there are no collisions, no motion, no nothing, all the atoms are concentrated in the same pixel of my experiment, then in this pixel, I could define this collective spin operator.
Okay.
And this operator is, well, by nature, by construction, it is quantum because it's the sum of many, many quantum
Spin
variables.
half. Yes.
Now, as long as there are no correlations between the atoms, as long as everything I do looks from the single atom point of view as the same, and I generate no correlations, I am in what I can call a classical state. And it would be, for example, all the atoms pointing up or all the atoms pointing to the side or somewhere. Once I introduce correlations, for example, if I take a light field, which is in a quantum state, and I map the state of the light field onto the spins, then I could put this spin in a quantum state. For example, a state where the uncertainty is not symmetric. That would mean then I would say that the spin is in a non-classical state.
Okay. Okay.
How do we generate this state? How do we interrogate it? So usually we do it using light. Okay.
Yes, but can you
And
still have this classical state where you can still think large S, like as you said, million spin half. So like value is half a million. So can you get that in for classical state, or is
yeah, most of the applications, if you think about this magnetometer, there is nothing quantum in this magnetometer, at least
okay?
from the point of view of the collective spin.
Mhm.
You pump all the spins upwards.
Okay.
It just generates a moment with a large spin. And
Mhm.
then you look at this precession of the spin, and your light interrogate the spin using Faraday rotation. All of these things happen on the classical level. If you want, this is a single atom physics
Mhm.
with just
Yeah, but
multiplying.
what I was saying that like for example, okay, I do not know the number of spins, but I'm saying the number of spins which will behave together, would it be million, or that also possible that you can get rid of all the collisions and all these by your pumping or any other mechanisms like reducing spin exchange collision and all these to behave to get something like it has half million spin moment or something like that is possible, you are saying that's what they do, you are
Yeah, let me mention that
uh,
all of this formalism
uh,
would hold as long as there is a macroscopic polarization.
uh,
So I need a macroscopic fraction,
uh,
ideally 100% of all the atoms pointing to the North Pole.
uh,
And I discuss only small excitations around the North Pole.
okay.
So to answer your question, I
uh,
would say that a square root of the number of atoms
uh,
is the number of excitations that I allow. And if the number of excitations in my, say, Fock state or squeeze state or whatever is larger than square root of the total number of atoms, then you might not be in the pure quantum regime anymore. Okay, so in terms of interactions that are spin exchange interactions, collisional interactions, things like that, you need to stay within the small excitation regime,
okay,
square root of n.
to get a collective behavior, I guess that's a
Exactly, exactly.
okay. Okay, very good. Okay, thank
Um, so just to explain to those that are less familiar, the way we flip a spin in alkali atoms is by, usually with light, is by exciting and de-exciting the electronic orbit. We take the electron, we excite it to, say, an orbital quantum number 1, and we use another light field to de-excite it. This is a lambda system. This is a Raman transition that flips a spin. And the reason the spin is flipped is because there is a strong spin-orbit coupling in the excited state. This spin-orbit coupling is strong. The dipole transitions here are strong. So this effect is effective, it's efficient, and it's very useful. It happens at the visible and infrared, so we use it always. This is our main tool to interact with the collective spin, to flip a spin, to interrogate the spins, like, for example, to measure spin noise, as we discussed before the talk.
you.
Now, this is done frequently and in many places. I could give you many examples. I brought here 2 examples that are nice because they come from both from last year, both from the same group, and they pertain each one to the different quantum states that I alluded to here. So kind of to be very brief, here there is a quantum memory where a detection of one photon heralds the generation of a Fock state in the alkali atoms in here. And this is a memory for a single photon. And on the other side, you see an experiment in which the collective spin of the alkali atoms is entangled to a macroscopic membrane, to a mechanical membrane. So this is a Fock state of one photon, and this puts the atoms and the membranes into a two-mode squeeze state. And so both of them are quantum in a different nature. Okay, that's good. So now we know how alkali atoms can function to do many interesting quantum optics things. Can we do the same for nuclear spins of noble gases? And here I talk about those kind of atoms that are on the right column of the periodic table. For example, cesium, neon, krypton, or helium-3. Helium-3 has 3 nuclei, so it's an odd number, and therefore it has a non-zero nuclear spin. So in this nucleus, there is a spin 1/2. And these spins are extraordinary, actually. And this is because they are enclosed, they are protected by the full electronic shells around them. And therefore, even at room temperature, if you put them into this cell and they collide frequently with the walls, even then, they do not lose spin coherence for a very long time. And I show you here measurements. So on the left, this is a collection of measurements published by the NIST group, where you see that the world record for keeping those helium spins polarized in a vapor cell is 4 months, T1 time. So you pump them once overnight, say, over a few days, and then you let go, and they keep their polarization for months.
And this is room temperature, I believe.
Probably elevated temperature, but it's not less than room temperature. Yeah.
Okay.
These are experiments we do in our lab. This is again at a temperature that is much above room temperature. And you see here the precession of helium-3 measured over hours. And the T2 time in this particular experiment was 2 hours. That's the decoherence time. So it's shorter than the lifetime. Maybe there is some inhomogeneity of the magnetic fields that we used and everything else. And still we are able to keep the spin alive. If it's a qubit, then we would keep the qubit alive for hours.
So what is the reason for decoherence for this system? Is a collision or what kind of mechanism?
So in our case, in this particular experiment, there is some contribution to collisions, spin diffraction collisions of the helium when it collides with potassium that is also inside the system. But the main limitation in here is simply inhomogeneities of the magnetic field.
Okay.
But this is very complicated. It's not simply the inhomogeneities of the external magnetic field, because the spins themselves also generate magnetic field onto themselves, onto the other species that are in the cell. This is called an effective magnetic field, EMF. And in order for this to be uniform, you need to make the cell very spherical. So there is a lot of geometry that enters this, push towards high coherence times.
So, Ofer, is this system small? Your diameter of this cell where you are keeping? Because what is the inhomogeneity of magnetic field you are talking about?
You're right. So the cell is about 1 or 2 centimeters in diameter. It's a spherical cell. The magnetic fields around it, there are multiple layers of magnetic field, and they are bigger, tens of centimeters. And then there at some point inside those magnetic shield, there is the magnetic coil to generate the magnetic field. So it's very, very uniform. It's uniform to the level of the inverse of 2 hours.
Mm-hmm.
And still it is a limiting factor.
Mm-hmm.
Now, these are exotic systems, but I mean, not too exotic. And if you look around, you see that people actually made applications also from these spins, not only from alkali spins. So I show you here two examples. If you inhale them to your lungs, when they are already polarized, then they don't even lose polarization in your body, and they stay polarized, and you can perform NMR measurements with no magnetic field or with very low magnetic field. You don't need to polarize your own nucleus. So the hyperpolarization is maintained when you inhale them. That's another system. This shows you that it could be a very small system that you can pack and put in real life application in the field. This is a gyroscope. It rely on the fact that these spins could point to one direction, and you can suppress their sensitivity to magnetic fields dramatically, such that at the end you get a dial, a pointer that points to a specific direction and does not lose this direction. And it's a very, very good gyroscope. So actually, if alkali atoms are the most sensitive magnetic field sensors that one can produce, then I would say that noble gas atoms are the best gyroscope, the most sensitive gyroscopes that humankind know how to build currently. They are very, very, very sensitive gyroscopes. So why not do our quantum optics with them? As simple as that. And of course, the reason is they do not have this nice spin orbit efficient coupling. In fact, they do not couple to light at all. There is no transition at the optical domain for ground state noble gas spins. So there is no way to do that with light, and we have to find a different way to couple to these spins. And that's what this talk is about. I would spend a minute zooming out also to show you some other regimes if we are anyhow doing this overview on alkali and noble gas ensembles. So if you take a broader look, I already mentioned to you the electronic spins and the spin orbit coupling in here, and noble gas spins, and this would have coherence times ranging from milliseconds to seconds. But there is another thing that you could do in ensembles of alkali atoms, and this is to go to highly excited orbitals. Maybe something low, some low orbit number and low angular momentum, or something very high, far close to the ionization level that is called the Rydberg level. And these are beneficial because they give us these interactions that I mentioned before. So just to give you a feeling, although we are going to talk about this, these are also possible. You could do everything I told you up to some limitations with those excitations. For example, you could generate quantum memories and entanglement and things like that. The only problem is that they live shorter. This is a microsecond to a nanosecond world lifetime. And given that these are the lifetimes, there are still a lot of advantages to do that, to work with excited atoms. So although they are shorter lived, the excitation of orbitals, for example, to this huge orbit, could be faster than exciting spins because orbit coupling is stronger than spin orbit coupling. It could be much less noisy. This is because all the colors involved are different, and you don't use two fields with the same color. And also because you excite states that are unpopulated, you don't work with a populated state when you generate coherence. So there are no thermal excitations of your quantum state. And also, Rydberg atoms provide for atom-atom interactions, which is another bonus. And indeed, another thing we work on in the lab is on doing quantum memories and sources and deterministic gates for photons using these orbital excitations. Let me skip that and move back to noble gases. Okay. So now we are in the very, very slow world of noble gas spins. Their lifetime is seconds, minutes, and hours. And we want to couple light to noble gas spins, but we can't do this directly because they don't couple directly. So the idea would be to put a mediator in between, an alkali spin ensemble. Then the light couples to the alkali via spin orbit interaction. And the alkali spins would couple to the noble gas spins by collisions. So they would simply collide inside a vapor cell. This is how it looks like. It's a glass cell, spherical cell, filled with a mixture of noble gases, these are the red atoms, and alkali, which are the green atoms. These type of mixtures are definitely not a new thing. They are really a tool that is used a lot. Um, People mix alkali atoms with noble gas mostly for these two purposes. First, in order to polarize the noble gas atoms. So the way it is done, you shine light into the medium. The light is circularly polarized, so it puts angular momentum into the alkali atoms and it pumps the spins of the alkali atoms upwards. And then via collisions, slowly but surely, this angular momentum is passed to the nuclear spins. This is called spin exchange optical pumping, or ZEOP, and it's very well studied. Another reason you would want to mix alkali atoms with noble gases is in order to probe the noble gas spins. I already told you that alkali atoms are very, very good magnetometers. And so if you put the magnetometer intimately with the thing you want to measure, which is the noble gas spins, you get a very sensitive probe. So people use these mixtures in order to measure the spin of the noble gas. All of these initialization and probing, they all rely on collisions. And this is a spin exchange collision. So all of the spin exchange collisions look more or less the same. The two spins approach one another. And when they are close enough, they process around each other and generate some angle between them. So this angle can be very small or very large. Sometimes, for example, when two electrons collide, they do many, many, many round trips around each other before they separate. It's a picosecond, it's a few picoseconds each collision. And still two electrons that collide due to the Coulomb interaction process around each other thousands of times. In contrary, when an electron collides with the nuclear spin, then this angle is actually very small. It's 10 to the minus 5 sometimes. But the basic microscopic collision look the same, mutual precessions of the spin around each other during the collision. So we have those mixtures in the lab. We use xenon and rubidium and helium and potassium. In this, I will show you only results from the helium potassium mixture. We make them ourselves. These are the cells. You see here, for example, how the helium process in the lab after it's been pumped for a night. So we pump them overnight, and then we come in the morning, and we give them a small kick, and we follow the precession of the helium nuclear spins, and you see that we get this 2-hour. Okay, so those mixtures are good. They have very high lifetime. You can initialize them. You can probe them. We want to do something else with them.
So
we want to.
Sorry, Ofer, maybe before you move, just trying to understand this exchange collision between electron spin of noble gas and electron spin of alkali atoms, right?
No, it's the nuclear spin of the noble gas.
So
the noble gas does not have any electron spin.
So because closed cell, you are saying that outermost electrons cannot interact.
Exactly. They have net spin 0.
Net spin, but what is the helium spin here? You are talking that the F quantum number, or what you mean by the spin?
So because there is an even number of electrons for helium-3, but there is an odd number of nuclei.
Okay.
2 proton, 1 neutron. And the 2 proton plus 1 neutron sum up to give a spin half. It's a nuclear spin.
So now nuclear spin is actually deep inside the atom, right?
Right.
So the coupling between electron spin of alkali and helium's nuclear spin will be much weaker. Is it, or
is it? This is exactly correct. What happens in a collision is that the wave function, the electronic wave function of the alkali, in our case, for example, potassium, it has a huge electronic wave function. It has many electrons. This collides with the noble gas, and it penetrates through the outer electrons of the helium, and it gets to the nuclear of the helium. And then during this trajectory that the helium does inside the wave function of the potassium, there is a very weak Fermi contact interaction. Fermi contact is the precession, the contact precession, the precession during the contact of an electron and the nuclear spin of a neutron or a proton, and this leads to this precession of the spins. Okay, I did not yet talk, and I will talk only very briefly on the nuclear spin of the alkali atoms.
Yeah. So what
These
happens?
are actually disturbing us. We would wish they wouldn't be existing, but they are.
So then, but in your, like, if I write a Hamiltonian, so I will only write interaction between alkali electrons and helium nucleus, and you are saying the other one, the nuclear interaction between helium and alkali is not important here, because they might be another order of magnitude smaller in coupling.
It's very weak.
And
it's not order of magnitude, it's many orders.
Okay, so just one curiosity, that what would happen, what would be the scale if I consider this thing rubidium and potassium alkali spins exchange collision versus the rubidium and helium electron spin nuclear spin collision? The rate, how they would be different? What is the scale?
There would be probably about 7 orders of magnitude difference in the spin.
Okay.
Electron would be very strong. This we will call strong collision. And electron nuclear would be very weak. This we will call weak collision.
So you will have 7 order different collision in this case, which you want to use it for your experiment, right?
I want to use the 10 to the minus 7. That's the problem. It's very weak, and still I want this to be efficient. Okay. And at the same time, I will require that the other collision, the one that is very strong, would not disturb.
Yes, because otherwise the rubidium itself can interact through their spin, right?
You are completely correct.
Okay.
I wanted to say something about this. So since you kind of you went through the terms in the Hamiltonian, I will mention that there is a term that you didn't specify, which is the coupling of the electron of the alkali to the nuclear of the alkali, nuclear spin. This is the hyperfine term.
Yeah, hyperfine, right?
What we do is we work in the in a regime where the atoms are pumped into something that's called the spin temperature distribution. And in this particular condition, you could eliminate this hyperfine term and think about the electron as just being dressed by a bit of a nuclear spin, which is, so the formulation is called the slowdown formulation. There is a parameter that's called the slowdown factor, which simply kind of represents the disdressing of the electron. And when you take this into account, you can forget about the hyperfine interaction. Okay. All right. So as I said, we want to now take this weak spin exchange collision and make it a coupling that is efficient, that is controllable, and that is coherent, that would couple these two collective spins. This is a bit mind-boggling because these interactions are weak and they are stochastic and they are random and everything is in the thermal ensemble, and still we require that they would be coherent. So not trivial, and several challenges are in front of us. Some of them we just mentioned. So let me start from actually the last one. This is the most conceptually not obvious. Can this random process of collisions, can this transfer non-classical correlations between the two gases? Can I start with a Fock state of the alkali and somehow couple this and generate a Fock state of the noble gas? Okay. Second, we want an efficient coupling. And that means that because each and every collision is very weak, as I said, it's like 10 microradians, we need many collisions. So we need to take the densities to be very high so that the collisions are very frequent. But when that we will talk also. And when the collisions are very frequent, then there will be, and when the density is large and the collisions are frequent, collisions between alkali atoms that are much stronger might pose a great challenge as well. And this is what we will start from. So we will start by discussing the lifetime of the alkali atoms in the presence of a lot of collisions, a lot of strong collisions. Um, Now I'm looking at the time and I see that we should at least choose one of them to be quick about, and I think I will choose this to be quick. So now let us kind of accelerate a bit, and then we will slow down when we get to the other two, which are more related to noble gases. This is alkali only. Okay. So just to give you a flavor, let me say right from the beginning that in principle, spin exchange collisions between alkali atoms should not cause any decoherence. They should not be a problem at all if there was no nuclear spin for the alkali atoms. In the absence of alkali nuclear spin, if I is zero, we should not worry at all. Why? Because these two electrons come into the collision, the electrons collide, the nuclear spin stay behind. They may persist around each other for a very, many periods, and this number is random because each and every collision is random, but still they would be in a triplet combination when they start, because to begin with, atoms are indistinguishable. They always point to the same direction because I address all of them at the same. So atoms start in a symmetric state, and the symmetric state is always a triplet. And therefore, no matter how high they climb in the collision potential, they would they would accumulate some phase. This phase could be very large, but it would be the same phase. So it would be kind of a global phase, which causes no decoherence. In other words, in the absence of nuclear spins, the electron spins always come in pointing to the same direction, and so they cannot precess around each other because they anyhow now point to the same direction. So no precession. The problem starts when you put the nuclear spins in, and then because of correlations inside the atom, there is a chance that these atoms would come into the collision in a singlet state. Or you could think about this, that there are correlations that are generated that exist before the collision between the electron and the nuclear, and after the collision, because the collision happens only between the electrons, these correlations are gone. And these dephasing between electron and nuclear spin during spin exchange collisions is the one that causes decoherence due to these collisions. And if you go to a random person in the community of alkali vapor, AMO, quantum optics, spin exchange is usually associated with relaxation. This is why spin exchange relaxation is something that we talk about all the time. And indeed, all of these experiments, and almost all experiments, the lifetime of the spins is limited by spin exchange collisions between the atoms. So what can we do? How can we get rid of decoherence due to collisions if we want to work with very high densities and very high collision rate? And the answer is that we need to somehow get rid of these correlations with the nuclear spin. So then, instead of working with this spin flip, which is something that people do a lot, this changes the spin by 2 quanta. Or working with this spin flip scheme, which changes the spin by 0 quanta, one should work with this spin. This scheme changes the spin by only 1 quantum, and it flips an electron spin, or it flips a nuclear spin, but it doesn't flip both because it's only 1. And therefore, it does not generate correlations with the nuclear. Whereas the other scheme, the regular schemes, they flip both. Delta m equal 2 or delta m equal 0 means that this transition flip together an electron and the nuclear spin in the same atom. And because I need to rush, I will skip other explanations of the same thing I already told you. So forget about this, but believe me that a triplet remains a triplet.
So Ofer, just one question. So you are saying even this configuration where you are saying that delta m equal to 1, so even that will reduce spin exchange collision even if you don't have any, let's take a helium atoms or all this noble gas. So this will
Exactly. This is alkali only.
only
And,
alkali, and
and
this configuration will increase the spin coherence time by lot. Means is that the references you are saying is for that increment due to this kind of proceed, means delta m equal to 1, that you have enhancement in spin lifetime.
Exactly, exactly. So I'll show you now the kind of experimental proof for that.
Mm,
What we did, we performed light storage
mhm,
using this scheme. So we stored the signal photon. It's a classical light storage, but it's quantum memory state of mind
mhm,
onto the spin, either in this scheme or in that scheme. The delta m equals 1 and the delta m equals 2. And we compared the lifetimes. Okay.
no, what is the difference?
So it's a polarization. You flip the polarization. You use different polarizations of
No,
the
I'm
field.
saying what's the difference in the lifetime you get
So
this?
these are the results.
Okay.
You see here the lifetime for the delta m equals 1 scheme and for the
Mhm,
delta m equals 2 scheme when you crank up the atomic density. So
mhm.
of course, for small density,
They are similar.
not many collisions. The
Mm,
difference is small, still almost an order of magnitude, but still
mm,
small even at this low density.
mm,
But of course, when the density gets high, the difference becomes larger. And in particular, our scheme is not sensitive to collisions. Collisions do nothing to this particular transition.
mhm,
Um, I will also mention that delta m equals 1 is actually the most simple transition you could think of, because this is the one that pertains to the orientation of the spin. So if you go and measure the orientation in the experiment, these tiny graphics are experimental data,
mhm.
you could see that you map the polarization state of the photon onto the full orientation of the alkali spins. And maybe that's another explanation for why this works, because if you orient all the atoms into one particular direction, there is no spin to exchange because they point to the same direction. And therefore, this is independent. This is free from spin exchange relaxation. And it's maybe important to stress that this is a U2 subspace, so an SU2 subspace.
Okay.
So this is a qubit. Okay, there
Mm,
are,
mm.
you see these ellipses. It has 2 degrees of freedom, so it's a decoherence-free qubit subspace on which one can write a qubit. So the full subspace is free from spin exchange collisions, relaxation due to collision. Okay, I will let me skip this data just for the sake of time. It's not crucial to the continuation. Okay. So now we are off to our second challenge, which is, well, okay, strong collisions do nothing. Now we require that these weak collisions do a lot. We want to see how we can efficiently couple the two collective spins of these two species, the noble gas and the alkali, using very, very weak collisions. Each and every collision only transfer about 10 to the minus 5 of the information. So to understand how this coupling efficiency could work, let us first remind ourselves what exactly is to be coupled efficiently. So I remind you, we start the experiment overnight by pumping the spins of the alkali, and through collisions, this pumps the spins of the noble gas until we get a macroscopic polarization of the noble gas, about 30% of the atoms. So this is in a pictures in our vector representation. It's the sum of all the spins. And I remind you, this is the total spin, the spin operator that we work with. And now we have a macroscopic occupation, macroscopic polarization. So there is this uncertainty disk with the square root of the number, square root of the length that determines the uncertainty. Now, this is a quantum operator, and this defines our quantum states. So for example, the ground state is all the spins pointing up. And then a singly excited state would be, it's a Fock state, would be lowering it by 1 quantum. So taking one of the spins and make them point down. The second excited state is, again, a superposition of this. It's a collective state with 2 spins pointing down, etc. So one
But
assumption is that
but
there
offer,
is this.
sorry, I still have this doubt. Why? So these are all room temperature experiment which you will talk, right?
Exactly.
So
But I remind you,
yeah.
this room temperature indeed is important
Mhm.
mostly for the external degrees of freedom. So the atomic motion is classical, it is
Yes.
thermal. The
Yes.
atoms occupy the whole cell and move around and collide randomly.
Yeah, but then
Also,
okay,
the
sorry, please.
occupation of the spin states, the internal
Mhm,
states,
mhm.
is at the basic level determined by the room temperature. So, for example, all the spin states in the ground state are equally populated.
Yes, very good. But then why do you write this superposition? Because like all the atoms, you are saying it's like it's forming a single state that that because I would expect that all atoms had their individual phase factor or not. Are you getting my point? That why should
So
I? Yeah.
imagine now, for example, that in order to simplify the notation on the slide, I
Mhm.
think about all the atoms as being located in a single pixel in my cell,
Okay.
such that their phases are all the same. So when I talk to them using light, they are within much in a region that is much smaller than the
Light
phase
wavelength. Yeah.
change, and therefore I put no phase term in here. Otherwise, I
Mm,
would.
uh,
It's not hard.
uh,
Okay, and then all of these atoms together form one big collective spin. And I cannot differentiate between the atoms, so all the states that I write, I need to write in the symmetric formalism. Okay?
Hello.
Yeah.
yeah. Someone has one question, maybe. Yeah, please.
Yeah, I have the same question actually. The thing is, for you to write the summation over spins of different particles, these particles need to be strongly correlated, and you are saying this is an ensemble. So how can you take this summation?
No, so I didn't yet tell you how I would generate this very um, correlated state. I agree that this is a fancy state. Actually, I don't think anyone um, knows how to generate this with very high fidelity. Um, but I'll give you an example. If you remember, I showed in the beginning this DLCZ protocol, this protocol in which you shine light on the atoms, you wait until you see a photon scattered, and when this photon is scattered, you know it was scattered from the atoms, so you know that now one atom is split. This protocol essentially generates this state, a state with all the atoms still pointing up, but one, we don't know which, but one is pointing down. So a DLCZ protocol is the way, for example, one way to try to generate such states. Okay.
So, but offer in you got one state, but when you wait for sometimes there will be spin exchange collision, and the spins of which you got in that superposition would change to another one, right? So over time, the state will evolve even between this. You are saying between this one which you call state one,
Yeah.
but still it will remain like one spin down and all up. Is that your main?
Yeah. I could, for example, one possible answer is that if we imagine the most simple case, spin half particles, indistinguishable spin half particles colliding with each other randomly in pairs, then if you notice, this is the sum of I is a symmetric state for all exchanges of all particles, whatever you exchange. So that means that any pair you choose out of this ensemble is in the triplet state because it's symmetric to replacing them. And if it's in a triplet state, then spin exchange collision does nothing to it. I remind you that when the atoms get into the collision in the same state, they cannot process around each other because they are in the same state.
So you
Begin with.
have to have this triplet in the begin with. That's what you are saying. If
Yeah.
it's triplet, then there will be issue because then.
Yes, if you have a superposition of triplets and singlets,
uh,
then they would decohere. So what
okay.
spin exchange does, it decohere it messes up, it dephases the
Yes.
phase relation between the singlet and the triplet.
Okay. Okay. I see now.
Okay, but as long as you are in a symmetric state,
Uh,
spin exchange is your friend, not the enemy.
okay.
Why is
Uh,
I'm saying friend because I will use spin exchange in order to couple this state from the alkali into a similar state in the noble. So it's friend.
Uh,
yeah,
Yeah.
hi, this is Sachin. I have an observation here and a question also. Hello.
Yes, yes, yes.
Yeah. So this spin down state is like, so in the ensemble of atoms, you have one of the spin like facing downward. So this looks something very similar to the NMR, this thing, wherein they use quantum, like NMR for quantum computing, wherein one of the nuclear spin goes down And so, and that is treated as a like a qubit state. So is it?
Yeah, I think so. I'm not sure because I'm not an expert for the NMR quantum computer, but I think in this type of kind of multi-spin structures, the spins are distinguishable. The spins actually, they could associate them with particular sites in the system. So the spins have flags. I'm spin A, I'm spin B, I'm spin C, and then A is a qubit, B is a qubit, C, etc. Okay. In our case, the atoms are not individually accessible, and they are in most cases they are indistinguishable. In the same pixel, they are all buried together. So I can only talk with symmetric states. I cannot individually address each other. So
but as an ensemble, this is a single. So 0 is 1 qubit and 1 is 1 qubit kind of thing. Like that
so the whole ensemble is a single qubit in my case.
Yes.
And well, it's a multi-bit. With 0 and 1, it's a qubit. Yeah.
And one more thing, if you could just go to the previous slide.
Yeah. Let's see. This one? Or even
one before that.
Even back, yeah. And even back.
This one. Okay. So basically, what you are doing is you are doing optical pumping, and then you are like elongating the relaxation time for the spin to decohere.
Yes.
Okay. So but in the figure over here, I see the paraffin coated cell is used. Like, so that also like, so this is adding to that increment of the decoherence time, or?
Yeah. So there are two main decay mechanisms in those type of memories, right?
Yes.
One is spin exchange, kind of it's a local mechanism, and the other one is wall collisions, which are this happens at the boundary. Okay. Of course, we need to suppress both. So we start off with.
Yeah, please.
So we start off with a paraffin coated cell that is coated extremely well. We only know one person in the world that does this. So we borrow the cell from this guy. And so this at least eliminates the boundary problem. Okay. And now, because in the experiment with the noble gas, we're going to work with very, very high densities, even much denser than this. We are climbing to 10 to the 14. So we're talking about like down below. We have to also eliminate the spin exchange dephasing. Okay. And this is done by doing this pumping and using this delta M equal 1 transition.
Okay.
So, Ofer, was it a joke why you said that only one person who does paraffin coating?
No.
It's very difficult, is it? Or
no, I mean it's so he is Misha Balabas. He started in Russia. He spent a long time in the USA, and then now he's back in Russia, and he has this art that he knows how to coat extremely well glass cells with paraffin or with other type of organic materials that preserve the spin and allow the alkali spins to collide with the walls 10,000, 100,000, and even 1,000,000 times without losing spin. I'll give you a sense. If you want like to keep this to 1,000,000, if we want to make sure that the atoms can collide 1,000,000 times with the walls without dephasing, we have to make sure that the coating coats at least 9, to 6 nines or to 5 nines. Okay, even if there is 1 to 100,000 area that is not coated well, the atoms will find it eventually and they will decohere. So one of these capabilities of Misha is to coat it to the million.
Just a point here, like Professor Butker also does a lot of work on this paraffin coated cells.
Yeah, that's the same cell, the same person.
Same thing. Yeah.
There is, I mean, Butker manages. Yeah.
Okay.
Yeah.
So what we are now doing, just to simplify the notations, we are performing a transformation of notations. We are using something that is called the Holstein-Primakov transformation, or the Holstein-Primakov approximation, which holds when there is a macroscopic number of atoms polarized, pointing up. And we define, instead of this lowering and spin operators, we define a bosonic operators that generate this bosonic ladder of states. So now we have A and A dagger that generate excitations, 1, 2, and annihilate excitations. These operators, this harmonic oscillator, quantum harmonic oscillator, that is the number of excitations of our collective spin, these are the operators that we want to strongly couple between the gases. I'll give you another intuition for these operators. If you look at their expectation value, the mean field, what you get is simply the macroscopic orientation of the spin. I already told you, and we discussed this a lot now, that the orientation of the spin is the thing that is the most preferable when you deal with spin exchange, because orientation is conserved under spin exchange. And therefore, A dagger is something that does not decohere very quickly during spin exchange. So for A and A dagger defined like that, spin exchange is a friend and not an enemy. Okay, so now we want to couple A dagger of the alkali spins to A dagger of the noble gas spins. So they are colored green and red, and A is alkali, B is noble. And we mix them together, so we have these two collective states. The coupling at the mean field level is something that people know for quite a long time now. And these are, Happer and Walker and Romalis have been pursuing that for many years. And in order to describe this on the classical level, this is not very difficult. One needs to perform this stochastic calculus. So you sum over stochastic random times for random collisions between random atom A and the random atom B. And each and every collision is described by a random angle, phi. And for this analytic treatment, you need to supply the calculation with the moments of your random variables, and in particular, the first and the second moment of phi. It's very important to note that phi is on average non-zero. So there is on average a direction for this precession, which can accumulate after many, many, many collisions into a macroscopic angle. Phi square, on the other hand, leads to fluctuations. And therefore, we want phi square to be actually small. So we want phi to be large and phi square to be small, which means we want phi to be small, right? Because the ratio eventually is what is important. And when people do that, and we did this also in the language of collective excitations, one gets this familiar form. So the accumulation of all collisions end up with coherent coupling between the alkali atoms and the noble gas atoms with this very standard spin exchange, beam splitter interaction, where spin exchange is the thing that coupled them. And there are other factors that determine the mismatch of precession frequencies. We control this by the external magnetic field and the decay, which we discussed a lot. And if you remember, there is alkali decay that is 100 milliseconds or a second, and there is noble gas decay, which is 2 hours, so I don't write it at all. Okay. Now, it's actually pretty interesting to look at how J looks like. So in this paper, we write this down in the language of collective excitation. And of course, it's linear in phi. So you want phi to be reasonable. But it is linearly proportional to the square root of the densities and the degrees of polarizations. And so in order to make J large, and what we want is we want to make J much larger than gamma and delta so that it wins and we get an efficient exchange between the...
So, Ofer, if I can ask you one thing about this equation which you have written. Okay, so why you are, I guess you start with not expectation, right? The variables which you start with, they are not expected quantity, because I guess this expectation is quantum expectation, or what is this? Are all these expectation quantum, or some of them are thermal expectation? Because like phi average, what you write, versus A dagger average, all are thermal expectation or some are quantum expectation?
I would say both. So when you, in the ideal case, you manage to pump all the atoms to up at the beginning. So you start with the vacuum state, okay? And you also neglect all of the depolarization mechanism in the ideal case, so that you are left with only dephasing or decoherence mechanism. In this case, you would still have gamma, because gamma is dominated by dephasing, okay? The depolarization mechanisms are much slower. And so then what is written in here is only quantum expectation values and quantum dephasing and everything, okay? Mixed state.
No, because my question is because of that reason. I was thinking phi expectation is over some realization or over thermal averaging, right? Because A would be more quantum as you were saying, but the phi, which expectation also appear in J, how are you getting that line? I'm a little confused.
You could think about this as, I could try to write down an equation for the operators themselves, not for the expectation values.
Exactly.
It's of course much more interesting, actually.
Yeah.
But then if you take the equation for the operators,
Yes.
and you look at only the first moment, the expectation value.
Yes, but then phi and A would be coupled. How you decouple them? That's the question.
I think so. No, so those brackets and those brackets are not the same.
Yes, so that's what I'm saying.
This is brackets in the sense of the stochastic formalism.
Yeah, thermal.
Per collision. Whereas these expectation values are per realization, per experiment. Okay? So there is a trajectory in the dynamics for the quantum operators A and B, and I take the average over all possible trajectories, which is maybe not the same as just these expectation values are kind of just stating the statistical properties of this random variable.
Okay, now I see, because the otherwise I got confused that how two expectation you are decoupling.
So, yeah, I agree. Maybe it's a bit confusing that I use the same. We actually in several of the papers we use a subscript C to represent the difference between them, but here I didn't put it. Okay. And so Didier, do you want to tell me what would be a good time frame? I'm happy to continue. It's just I wonder what's the
okay, let me see what's the time. Just 1 minute. Okay. So it's 5. So maybe another 15 minutes is fine, I hope.
Perfect.
Yeah.
Okay, good. Excellent. Okay. So what I want to show you is that we now are able to get experimentally to the regime where J is much harder than gamma. That was one of the big questions when we started this work. And the knob is mostly increasing the polarization degrees and the densities to a level where J becomes large, and decreasing gamma to a level where it's small. And I showed you that we now got to this gamma equals about 10 hertz, which is a world record.
So, sorry, I still don't understand where this nucleus of noble gas and alkali coupling enters here in J through phi. Is that the phi is the variable which takes care of the interaction?
Should I go? Maybe I should go through this expression. What do you say?
Okay, please.
So phi is a property of the species. If you give me the names of the atoms, say potassium and helium, and I tell you what phi is.
Okay.
It's a single collision property. V and sigma is a cross section for collision, and V is a relative thermal velocity. They together represent the frequency of these collisions. So the frequency times the angle per collision give you kind of a rate of angular mutual rotation. But this rate is you can collectively enhance it.
Yeah.
If the states that are coupled are already collective states and not single atom states, then you can collectively increase the rate by a huge factor, because our densities are very high, up to the point where it becomes macroscopically large.
So now this number is not which you were saying that 10 to the power 7 times smaller between alkali versus alkali noble gas.
Right. Yeah. So J is now much larger. This brings back all the 10 to the 7 orders of magnitude that are missing.
Okay.
7. So this is the experiment. I remind already from the start, this is a classical experiment, not a quantum one. Therefore, the expectation value in here. We use helium at 3 atmospheres so that we have a lot of helium atoms. And we heat up the cells to 200 degrees Celsius so that we have a lot of potassium atoms. And the experiment starts at night before the day ends by pumping all the atoms, the alkali and the noble gas spins upwards. And then we come in the morning and they are all pumped and ready for the experiment. And what we do, we give the alkali atoms a small kick using some finite pulse of magnetic field, transverse magnetic field. And we monitor the alkali spins using light, using Faraday rotation. So we look at what the alkali spins are doing. If indeed there is a strong coupling due to spin exchange between the collective spins, what we expect to see is that this excitation of the alkali atoms is transferred, hopefully transferred fully to the noble gas spins, and then goes back to the alkali and goes back to the noble, and back and forth. And indeed, this is what we see. What you see in here in red is monitoring the number of spin excitations, the alkali excitation, versus time over 20-something milliseconds. At some point it goes to 0, and then it goes back up, and goes to 0, and go back up, and continues. And what we also do, we do an experiment that is takes much more time, and in each and every point in here, we stop the dynamics, and we use the alkali atoms as magnetometers for the noble gas in order to measure the noble gas excitations. And this is the blue data that you see. The blue data is an indirect measurement of the noble gas excitations. And you see that they are the opposite of what the red shows, and that means that the excitation goes back and forth between them. And you see several periods over the lifetime. And you could show that this is about a factor of 10 between J and gamma, which means we are in the strong coupling regime now. And another way to see it is to take the Fourier transform of these frequencies and to repeat the experiments for different magnetic fields. So detuning away or changing delta, putting these into resonance and out of resonance. And then we get this data that shows you that by changing delta, we change the eigenvalue of the alkali. We almost don't touch the eigenvalue of the noble gas because the gyromagnetic ratio is much smaller. But then on resonance, there is a gap, and the gap is much stronger than the width. And that means that we are in the strong coupling region experimentally now. Good. So now,
sorry, Ofer. So you are probing these alkali atoms. Is it like the simple this pump probe which you do, or what kind of probing for this? Yeah.
In this experiment,
Yeah.
it's even simpler. This experiment is what you do in the experiment you told me about. It's a linear probe light that passes through the medium, and we look at the rotation of the probe light.
Because it has polarization, so it just have Faraday rotation, and
It's
you just
Faraday rotation far off resonance.
Okay, and you probe its relaxation, Faraday rotation in time. That's only you are doing. And then this Faraday rotation of alkali atoms is used to get the noble gas. Is that what you are
Yes,
saying?
and then for the blue data, what we do, we stop the dynamics. We can halt the dynamics at any point by increasing the magnetic field substantially. So by moving from the resonance to say very decoupled regime. So we can decouple the two gases when we want. What we do, we decouple them at each and every point.
Okay.
And we then monitor the alkali in a magnetometer scheme.
Okay.
So when the alkali is probed like that, what it measures is the magnetic field that is generated by the noble gas, and this allows us to measure the noble gas.
So this you have to then repeat again and again to get each point. How do you do? Yeah.
I repeat.
Okay.
This is done over one day. It's not,
okay.
It's not very complicated. Maybe I should already mention that this is already half of what you need for storage. So what I showed you is that I can now take an excitation from the alkali, pass it to the noble gas, and at that point decouple the spins by halting, by increasing the magnetic field, and that's it. Now it is stored on the noble gas, and I can wait, and I can turn it on at a later time and read it out.
So the
Okay.
increasing magnetic field would not change the dynamics of the helium, because they also have nuclear spin, as you were saying. So that
Yeah,
will
I
not.
mean, it would change the gyro, it would change the Larmor precession of the nuclear spins, but I know how much it changed.
Okay.
So yeah, it would, increase this omega and this omega, and then I come back. Yeah.
Okay.
There was another question.
No, I don't have any.
Okay.
Okay.
Okay, so we are efficient, and now the only thing left for me to show to convince you in the next 5 to 10 minutes is that this is indeed quantum. It's not only the mean field that is coupled and the orientation that are precessed around each other, but actually all the non-classical correlations can also be transferred. And some of you maybe are already convinced totally that this is the case because it's a coherent process. So of course it couples the harmonic oscillators, quantum or classical. Some of you maybe are not convinced, and let me make you even less convinced. Let me give you like a non-intuitive process. Suppose I started with indeed the alkali excited, but I only put the alkali in the Fock state number 1. All the alkali atoms point up, one of them, I don't know which points down, but only one. So now what I demand from these stochastic random collisions is that at a fixed time in here, this single excitation passes deterministically fully to the noble gas, and it generates one noble gas that is excited. And then at a later time, it passes back deterministically, and now the alkali has a single excitation, noble gas have exactly 0, and etc. And this is mind-boggling. How can I take 1 out of 10 to the 15 atoms, excited, pass it exactly so that 1 out of 10 to the 20 noble gas atoms are excited, etc. Okay, not easy, at least to be convinced. So let me try to convince you. So maybe less convincing, but at least kind of the background. This theories, analytics, writing down the dynamics or the evolution of the collective spin operators in a thermal gas is something that we and others are doing all the time. Imagine you have a spin operator. This could depend on R, so it could have also the phase relations that Debbie and Du mentioned earlier. We know how to describe the quantum noise, so the whole quantum dynamics of these operators when they experience collisions with the walls, when they diffuse in space, and R spreads, and also under spin exchange collisions. Okay, here are some theory papers and another experiment that shows collisions for 2 alkali species, and these models are fully quantum. They give you the full description for the quantum noise with fully polarized atoms or not fully polarized atoms, and they are numerically tractable, so you can actually explain with them experiments and study experiments even when there are spatial features, etc. So we know how to describe them, and indeed, if we do that, and if we follow the full quantum mechanical treatment, and for example, we define modes of diffusion and couple different modes in the quantum with the quantum operators, we get at the end an equation that looks exactly like the equation you already saw and that we proved in experiments, but now without the expectation value. So the same equation you saw is also valid at the level of the operators, only now it has quantum noise that is associated with it.
And
Okay?
I believe the J, you are using the same expression with expectation.
Of course, of
Okay.
course, yeah. And coming from this field, it's obvious that if it worked, I mean, I'm not surprised that this is the case, right? It's just one now needs to go to the quantum noise and see that this does not introduce too much noise. But this maybe is not convincing. This I just told you that it works.
But Ofer, how would you separate between non-commutativity of operator in your experiment? That let's take, you are saying everything is quantum. So what is the classical regime? How will you go to that classical regime in terms of saying that, okay, non-commutativity of operators, because you are now introducing quantum noise versus, let's take, I say everything was classical noise. So how will you separate?
Yeah. So I don't know. Maybe it would help to mention that these quantum noise operators, for the ideal case of a fully pumped ensembles, so when the polarization degree is exactly 100% for all the spin species, these are all vacuum noise operators. Okay, so it's kind of easy to take to the classical limit. It's not hard otherwise. Otherwise, it's a thermal noise. Maybe something I would mention, which is important, is that even if the spins are not fully polarized, but they are still macroscopically polarized, so it's tens of degrees, then the addition to the vacuum part is not large. It's moderate. It's on the order of the vacuum part. So even if you can only like pump 50% of the atoms or 30 and not 100, you would suffer from maybe 2 times more noise, or at the most 10 times more noise, but it's not a deal breaker. It's not a billion times more noise because billions of atoms are not polarized or something like that.
No, I understand about the noise you are saying, but I'm saying the noise quantum nature versus classical nature, can it be probed through experiment or tested that the noise is just thermal, not what you are saying, the vacuum noise or something which is quantum in nature? Is it possible?
So I would say, fluctuation, dissipation, whatever is dissipation can be probed. So for example, one of these Q operators describe the collisions with the world. Okay.
Okay.
The part that makes generates dephasing and dissipation of this coherent spin, this of course is this is what we probe in the classical experiments. The part that generate fluctuations probably I don't know, probably cannot be done in the.
Okay, so I'm saying that if you have written the same equation, instead of quantum noise, it has a non-commutativity, means it's a classical noise. Would it change your result, or would it matter that if you are using quantum noise versus classical noise? That quantum noise means it has a non-commutativity versus in terms of operator versus classical noise, which don't need that thing. So I'm saying, does it matter in your experiment because you want to say that it has quantum nature in terms of the noise, or if I'm not wrong?
I am not sure I know what to answer.
Okay. Okay, maybe I have to think also.
Okay, so I wanted to convince you about, at least show you another indication that indeed I can mediate quantum correlations. And what we did for that is we did a very modest simulation. So this is a many-body simulation with 100 electron spins and 10,000 nuclear spins, green and red. And in each simulation step, we choose randomly 2 of these atoms and we collide them together with a random angle, with a random spin exchange angle. And what I will show you is the result of such a run, and I will compare 2 initial states, 2 cases. In one, the initial state is all the spins point up and 1 alkali spin point down. And it's one particular spin. So for example, spin number 1. In the other case, I also start with all the spins point up. And also I put 1 excitation on the alkali atoms. But here I don't put it on a single specific alkali atom, but rather I generate this collective state, which is a superposition of each and every atom has a chance to be the one that is excited. And now I run the simulation with these 2 boundary conditions. And at the beginning, after 50 collisions, you see almost no difference. In the 2 cases, this electron spin is just lost to the noble gas spins. But if I run the simulation further, and now you see 5,000 collisions, you see a striking difference. You see that in the first case, when it was just 1 single excitation, it's kind of classical because we know which atom it was. Then this spin simply, by random collisions, is lost to the noble gas, which kind of functions as a reservoir because there are many, many, many noble gas atoms. So at the end, there is a chance of 1% that it will remain in the alkali and 99% in the noble gas. That will be the end of it. In the other case, on the other hand, these stochastic collisions, random pairs with random strength, actually generate some collective effect, a coherent effect, sorry. It's very, very quickly, the alkali very quickly loses the spin and gets to 0. It all moves to the noble gas, and now there is one and only one excitation on the noble gas atoms. And then it comes back. So indeed, the simulation shows that what this generates, the dynamics, is a coherent coupling between this collective Fock state and this collective Fock state. And in this simulation, there is nothing else. It's a super simple simulation.
And what determines the decay here in this?
Yes. That's what I'm saying. There is no decay that we put into the simulation by hand. Gamma is 0, per atom. In principle, it should last forever. The reason this decay is because of the randomness. So the randomness does introduce fluctuations, which causes dephasing. And the rate is described by the models and also easy to guess. The rate is given by the second moment of the phase. If you want the part that represents fluctuations, as opposed to the oscillations, which come from the first moment, the mean. So you see here what's the secret ingredient of all of this lecture. The fact that phi is small, the fact that each collision is very weak is crucial, because only when phi is small, you could get to the point where the accumulation of many phi is large, whereas the accumulation of a lot of phi square is small. Or if you want, phi square is much smaller than phi when phi is small. That's something that is in the backbone of many processes that we know, motional narrowing, for example, and other of those type of processes where multiple frequent changes in some inhomogeneous system actually retrieve the homogeneity, retrieve the coherence, and narrows the spectrum of the process. Okay. So with that, I probably need to wrap up. I will mention that in the next step, we are now putting light into the mix, because remember, we wanted to do quantum optics experiments. So you could think about an alkali atom with some optical transition that is used to manipulate its spin, and then the spin exchange interaction that couples the alkali to the noble gas. So your naive approach would be couple light to the alkali, turn on the interaction with the noble, wait an hour, I don't know if it's a quantum memory, then read it out from the noble gas to the alkali, and then read it out from the alkali to the light. That is the naive approach. The non-naive approach would be to do these two processes all together. So, turn on the light and the coupling at the same time. And if you want, if this state is not important to you, if you want to couple directly the light onto the nuclear spins without stopping by in the alkali, because the alkali atoms are just a mediator, you don't really need them, you could actually detune them away. Just like in a Raman transition where you detune away the excited state. So then the process from light directly to the noble gas, or indirectly to the noble gas, is a coherent process. This is done in this experiment, which is also available. And what I'll show you is the two sides of the coin. It's a bidirectional interface. From one hand, we can perform spectroscopy on the noble gas spins. So this is all optical spectroscopy. And you see that there is a strong attenuation of the light. It's a strong contrast. It has a very, very small line width. So it's a 10 millihertz optical spectroscopy at above room temperature, which is very narrow. And it's coherent. It's associated with this phase curve, which we can also measure. So it's a coherent optical spectroscopy, which is exactly what we need if we want them now to generate this optical transduction. The other side of the coin is this, and this is the fact that we can now coherently and optically stimulate the nuclear spins. we can send light and use the light to flip the spins of the nuclear, despite the fact that these nuclear spins are transparent to light because of the alkali atoms functioning as virtual mediators. So we never stop at the alkali atoms. They can be adiabatically eliminated, but they are there. They provide for decoupling. We can excite the nuclear spins when we are on resonance using light.
So this is nuclear spin of helium, you are saying, right?
Yes.
Yeah. And also when you are saying optical spectroscopy, is it again like the similar experiment which you were saying little early for measuring the oscillation, like that type of things one has to do, or how you do this experiment?
This particular experiment is done in actually a scheme that is not very well known. We're not sure if anyone use it. Maybe we are the first one.
Okay.
We're checking. We are modulating the polarization of the incoming light, and we are demodulating on the outside and measure only the S2 quadrature. If anyone is interested in this particular unique scheme, it's described in this paper and in details in the supplementary information of this paper. And I don't know if anyone knows, but there is a suggestion by Ignacio Zirac and Eugene Polzik to have a double pass configuration through a cell and therefore get quantum memory on orientation of spin. And this is half of the Zirac scheme. So if you look at the scheme by Zirac, this is implementing half of it. We think it's unique. We think this was not yet used ever. But I don't have time to get into that.
Okay. So I'll look at your paper. Okay, thank you.
So to summarize, here is the outlook. We want to implement storage of light on noble gas spins. And of course, probably the best way to do that is to using this adiabatic elimination regime, where the alkalis are virtual mediators. And these are described in these papers, these ideas. And then another experiment we work on is to get an entanglement of two noble gas cells, two noble gas ensembles, by shining classical light through both of them and measuring the polarization rotation in a way that gives you a sense for the sum of the two nuclear spins of the helium spins in here, but not the difference because you measure them both. And by this, you put the two helium spins into a two-mode squeezed state, which is an entangled state. This is done by Eugene Polzik in alkali atoms. And we have worked out with Eugene an idea on how to do this with the noble gas. So that is the outlook. And with that, I'll finish. Two things. So first, I want to thank the fantastic people who worked on these experiments. Or Katz, that started it all right from the beginning, and is now a postdoc in doing trapped ions in the US, so no longer hot atoms. And Roy Shacham, who is the senior PhD now on this experiment. And the second, I call you, everyone that listen that are in the level of PhD or postdoc. If you're looking for a PhD or postdoc, we are interested. Call us if you're interested in any of these type of experiments. Write me an email.
All right.
That's it. Thank you.
All right. Very good. Thank you very much. So if there is any question now.
Hi, this is Sachin again.
Hi.
Yeah. You were talking about dressing of the electronic spin with the nuclear spin, like to take care of the hyperfine interaction in the alkali.
Yeah. So you're asking about the hyperfine interaction?
No, the dressing, like, see, dressing in the like regular sense is like talked of
Yes.
an atom photon interaction, where the photon basically dresses the atom and the atomic levels get shifted by what is called light shift and all. So here what you are saying is like the electronic spin and the nuclear spin are they are dressing each other, or something. Like I could not understand that particular thing.
So just to make sure that oh, sorry. Where were we? So you're asking about this, right?
Yeah.
Yeah. So the way you could understand, maybe there is, yeah, maybe we look at it from here. So the way you should understand this is um, once, so before we send on the signal light, once we detune away this coupling, we could eliminate this level. Okay. Now, now instead of having J, we would have something like J square over delta.
Okay.
Or if this is an omega, then the two photon, it's not a photon, but the kind of, the two transitions would become omega times J divided by delta, similarly to what we call two photon Rabi frequency.
Yeah.
Right?
Yeah.
And this would be the new rate. So you could, if you eliminate this, you would get an effective erode that does this.
Okay. Okay.
With, with the strength J times omega divided by delta. It's not as fast as J.
Yeah.
But it eliminates the need to be faster than gamma. So of course we know from Raman transitions and from many other processes that this is the way to go. This is all. I mean, often you win. You see this, by the way, in here. Eventually, what limits the line width in here still is the alkali atoms. So despite being very detuned, there is still some J square over delta square times gamma A that is injected into the helium state. And this, a bit of an injection of decay due to this dressing, is still much larger than gamma B. This is, I remind you, hours or many minutes.
Okay.
And this J square divided by delta square over gamma, we can measure. This is this curve.
Yeah.
Okay? So we can detune away, and we get less and less and less decay. Yeah.
Okay. Okay.
Anyone else on this or any other topic I mentioned?
Is there any other question? Okay. I see not. Or okay. Okay. All right. So I see there is no more question. Okay, so anyway, Ofer, you talked for long, already 1.5 hours, and thanks again for this so nice talk and lot of interesting things. Maybe we should read also some of your paper first.